All right, seems to be fixed. So what we're going to be talking about today is our last lecture on this transient analysis portion of the class, which means I believe Monday is the date that I have set aside for you guys to ask questions about test number 2. So what we're going to be talking about today is more second order general circuits, but in this particular example that we're going to work, we're going to have 2 of the same energy storage element, but they're going to be independent. So the circuit that we're going to be looking at is this one here, where we have a voltage source. Okay. Let's just call this VS. I'm going to have a switch. And this switch is going to be closing at t is equal to 0. I'm going to connect it to some resistance R1. And down this branch, I'm going to have an inductance L1. Then over here, we're going to have a resistance R2. And we're going to have an inductance L2, like so. And what we are going to wind up trying to do here is we are going to attempt to solve for our inductor currents. So I'm going to call this I1 of t. I'll call this, this is being difficult today, I2 of t. This will be our voltage, V1 of t. Over here, we have our voltage, V2 of t. And instead of taking the approach that we did in our last problem like this, I'm going to intentionally work it differently. So I'm going to use mesh analysis to show you how that could be applied. And obviously, KVL could also be used if we were so inclined. Or excuse me, nodal analysis could also be used if we were so inclined, sorry. So I'm going to define my first mesh current here. So I'm going to call this current Ix of t. And the current around my second mesh will be Iy of t. Okay. So writing a KVL equation around our first mesh or mesh X during the transient condition is going to wind up giving us negative Vs plus R1 times Ix. And now we are going to have effectively, now we need the voltage drop across our inductor. So the voltage drop across an inductor is L times the derivative of the current flowing through the inductor, right? So L, I'm going to do d by dt here. Well, the total current flowing through the inductor in terms of our mesh currents is Ix minus Iy. Like so. Let me move this dt over because that's looking a bit ridiculous. So this is going to be equal to 0. And when we write our KVL equation around mesh 2, we're going to wind up having L1 times the derivative of IY minus IX with respect to time plus R2 IY plus L2 times the derivative of IY with respect to time is equal to 0. So what we're going to try to do now is isolate things here. So we're going to take this first equation and we are going to rewrite it slightly, right? So I'm going to call this equation here, equation 1. And what I'm going to do is I'm going to split, I'm sorry, there should be an L1 here. I'm going to split that derivative up, right? Because that's the derivative of the difference of two functions, which should be the derivative of IX minus the derivative of IY, right? So I could, rearranging that thing, I could have this expressed as negative VS plus R1 times IX plus L1 times the derivative of IX with respect to time. And I'm going to move that L1 times the derivative of IY with respect to time over here by itself. And to make things, actually, let's leave this as is right now. If I need to, I can move something over here in a minute. Okay. So this is just one rearranged. And I'm going to do something similar for problem, or excuse me, for equation 2. Our second KBL equation, right? So I'm going to put all of my IY terms on one side and all of my IX terms on the other side. And so what that's going to give me is L1 times the derivative of IX with respect to time will be equal to L1 times the derivative of IY with respect to time plus R2 times IY plus L2 times the derivative of IY with respect to time. Okay. So this is 2 rearranged. All right, so now we need to think about what we're trying to do here, right? Our ultimate goal is to wind up getting a second order differential equation here. in terms of either ix or iy. So I'm just looking at things here. I have a relationship for just the derivative of iy is equal to a bunch of stuff in terms of ix. And I have a relationship for the derivative of ix in terms of a bunch of stuff related to iy. So I'm trying to figure out how I'm going to wind up getting my second order differential equation. So actually, sorry, I just realized I made a mistake here. This guy right here should be an L1 because it's coming from this equation. So let me make sure I got all my other coefficients correct. Okay. So let's do one more edit to this equation 1 rearranged. If I divide through by a factor of L1, I'll just have this guy right here. And so I have the derivative of iy with respect to time is equal to everything over here on the left. Trying to think about how that helps me here. So I'm just thinking about what I need to do here. This one is a little bit tricky. So what I'm thinking about doing is taking the derivative of equation 2 rearranged, because my problem that I'm facing here is effectively that I have something for the derivative of iy, which is great because I could plug that in here and I could plug it in here. But what I don't have is a relationship for just iy by itself. And generally speaking, I try to avoid doing integration if at all possible, right? So if I were to take the derivative of the second equation, let's go ahead and do that here. So that's going to look like L1 times the second derivative of ix with respect to time squared. That would be L1. I'm going to group some terms together here. Plus L2 times the second derivative of iy with respect to time plus R2 times the first derivative of IY with respect to time, right? And I can get the second derivative of IY with respect to time just by taking the derivative of this equation 1, right? So let's call this guy 3, and this was simply the derivative of 2 with respect to time. We take the derivative of 1, we are going to have d squared IY with respect to time is going to be equal to 0 because the derivative of that constant term is 0. Then I'm going to have R1 over L1 times the derivative of Ix with respect to time plus the second derivative of Ix with respect to time. Let's call this 4, and this is simply the derivative of equation 1 with respect to time. And now I should be able to substitute 1 and 4 into 3. All right. So I have L1 times the second derivative of Ix with respect to time is going to be equal to L1 plus L2 times the second derivative of Iy with respect to time. So that's just equation 4. Plus R2 times the first derivative. Where the first derivative relationship is just equation 1. So that's going to look like negative Vs over L1 plus R1 over L1 times Ix plus the derivative of Ix with respect to time, close brackets. All right, so now everything is in terms of Ix, so I should be in relatively good shape here. So I'm going to move my constant term to one side of the equal sign. So I'm going to put my constant term on the left. So that's going to look like R2 divided by L1 times Vs will be equal to. So now let's look at our second derivative relationship here. So we have L1 plus L2 times our second derivative, and then we're going to subtract L1 times our second derivative. So that's just going to look like L2 times d squared Ix with respect to time. So that's taking care of this term right here and this term right here. For my first derivative, I'm going to have, excuse me, that should be in black. So let's see, I have L1 plus L2 times R1 over L1. So that's from this guy right here. I'm also going to have R2 that's from this term over here. I already moved that constant term over. Yeah. Times the derivative of Ix with respect to time. And let's see, the last thing that I'm going to have is plus R1, R2 divided by L1 times Ix. So if I've done all my algebra correctly, which might be a stretch here, this one was a little complicated. I'm in a really good spot to be able to solve for alpha and omega naught, right? So the last thing that I'm going to do is I'm going to divide both sides through by a factor of L2. So that's going to give me R2 over L1, L2 times Vs, excuse me. Is equal to the second derivative of Ix with respect to time plus, so let's see, this is going to look like R1 times L1 plus L2 over L1 times L2 plus R2 over L2. Times the derivative of Ix plus R1, R2 over L1, L2 times Ix. And from this, alpha will be 1/2 times the coefficient of the first derivative term. Trying to think if there's a way to pretty that up, but not really. And omega naught would be the square root of R1, R2 over L1, L2. And so from here, we could go through our normal steps. If we were given numbers and all of that kind of good stuff, and figure out, whether the response is overdamped, underdamped, critically damped, etc. So let's assume that we did all that and we were able to come up with a mathematical expression for Ix of t and Iy of t. How would we tie those two quantities back, our mesh currents that we developed our differential equation for? How would we tie those back to our inductor currents? Any thoughts? Well, hopefully we can see that our inductor current I1 is simply Ix minus Iy. And our inductor current I2 is simply Iy, right? So if we are able to write a second order differential equation with respect to those mesh currents, we can then tie things back to our original quantities of interest. Okay. In my personal opinion, applying Kirchhoff's voltage law around this loop and applying KCL at this node, it would have given us the exact same second order differential equation relationship. But to me, that would have actually been a little bit easier than doing mesh analysis here. But I was trying to illustrate how you can employ mesh to work problems like these as well. All right, so that's really all that I wanted to talk about for today. Like I said at the beginning of the class meeting, Monday's class will be for asking questions regarding the second exam. So if you have any questions, I'd be happy to answer them. If you have any questions now, I'd be happy to answer them. If you want to shoot me emails over the weekend, I'll answer those questions as well. So unless anybody has anything else to do or to ask about, I will see you guys on Monday.